Now we move to the next topic, that is disaccharides. So what were disaccharides? Disaccharides were those carbohydrates which on hydrolysis give two or more monosaccharides. So we are going to see a good example of disaccharide, and that is sucrose. Now, since disaccharides are made up of two or more monosaccharides, so this sucrose will of course be made up of two monosaccharides or more. So sucrose is actually made up of two monosaccharides, and they are namely the glucose and fructose. So now we're going to draw the structures of glucose and fructose. So let us just see. We have a CH2OH over here. Then we have an H over here, H and OH. So this is the cyclic structure of glucose, and we are very well aware how it is formed. That is, when the lone pair of oxygen was attacking C double bond O, we were getting this particular one. Now here in this particular glucose, we are going to be using the alpha form. And what was the alpha form? The alpha form was that the OH were cis to each other. The first and the second one were cis to each other. Now what are we talking about? See, this OH and this OH are cis to each other, and therefore we now call this glucose as the alpha D glucose. So we are using alpha D glucose as one monomer. Now these both are monomers. Please remember that also. That is, they're the units with which we are going to be forming the sucrose. Now, since we're done with the alpha D glucose, let us see the second monomer with that we are going to be using, that is fructose. Now in fructose also, let us first just complete the valencies. This is H, this is CH2OH, and this was also formed by the attack of lone pair of oxygen, and we get a cyclic structure after that. So in fructose also, we remember that we got two cyclic structures. One was the alpha D fructose and one was the beta D fructose. So what was the difference between them? In the alpha D fructose, we had the OH and the CH2OH lying at cis position to each other in the first and the second carbon respectively. And in the rest, that is the beta D glucose, we had them lying at trans position. So all the CH2OH as well as the OH were lying at trans to each other. So now in fructose, we are going to be using the beta D fructose. So CH2OH and OH. Now here we can clearly see that this OH and this CH2OH are lying at trans to each other, and therefore we can call this fructose as beta D fructose. Now D, we know the D configuration is because that the OH on the last chiral atom was lying at the right hand. So now we are done with our monomers and we have got both of them, that is alpha D glucose and beta D fructose. Now what we are going to see first is that in both of them we have the anomeric carbon. So we have got anomeric carbon at these two places. That is, the because of this anomeric carbon, we classified this glucose as a reducing sugar, because this anomeric carbon, this particular anomeric carbon over here, both of them are anomeric. Please remember that. So we have got anomeric carbon over here, and now what is going to happen is that these anomeric carbon, because of the presence of them, we were getting alpha D glucose as a reducing sugar, because due to the presence of this OH, this particular OH over here, and this the H can shift and we get a double bond, so we get an aldehyde over here, and this aldehyde was getting reacting with Fehling solution and the tolerance reagent, and we know that when a carbohydrate reacts with a Fehling or a tolerance reagent, then we call them as reducing sugars. Okay, so now we now know that these two carbons are called anomeric carbons. Now if in any case we destroy these anomeric carbon, then the carbohydrate will not be reducing anymore. So what are we trying to say is that if this anomeric carbon is somehow destroyed, then our carbohydrates will not be acting as a reducing sugar, because it will not give the tolerance reagent test as well as the Fehling test. So now how is the sucrose formed? The sucrose initially before hydrolysis, when before we are getting alpha D glucose and beta D fructose, the sucrose existed as one molecule. And how is that? With the use of this alpha D glucose and beta D fructose, what we're going to see is that if we convert them into the respective disaccharide that was present beforehand, so there is one slight change that occurred, and because of that, we are getting a disaccharide. Now, see, this is an O, and what actually happened was, since there are two groups lying on here, the rest of the molecule remains the same. So we have got CH2OH, H, HOH, you know the drill. It's the same, the rest of them remain the same, but we are only changing them at one position. And where is that? Now, if we draw this fructose, this beta D fructose, what we're going to observe in here is that when the disaccharide is formed, see this H, this CH2OH are lying at their places, but now what is happening is that this H of this OH as well as this OH are losing. This molecule is losing them, and when these are lost, we are only left with an O here. So what is now we're getting? We're getting an ether bond now. I'm just going to complete all the valencies so you don't have confusion regarding the structure. So the structure looks exactly the same. The only change is that now we've got this over here. And what is this? This is the ether linkage. What do we call it? This is the ether linkage, and the ether linkage which joins two monosaccharide units is known as a glycosidic linkage. So when these two alpha D glucose and beta D fructose were combined together, when joined with an ether linkage, they form sucrose. Now this is nothing but sucrose for us. And what actually happened is that a glycosidic linkage is being formed, and we're going to just be writing what is a glycosidic linkage. Now, a glycosidic linkage is nothing but an ether linkage between, or we can say joining two monosaccharide units. That is all we have to remember. So any ether linkage which joins two monosaccharide units will be categorized as a glycosidic linkage. So here, this particular linkage over here is a glycosidic linkage. Now we know that the first carbon over here in the previous case, like here and here, we knew that these two are the first carbon respectively, and these two, what they were anomeric carbons. So which were anomeric carbons we have to decide. So the C1 of alpha D glucopyranose, we also call this as the glucopyranose because of its resemblance with the pyran structure, and the C1 of beta D fructofuranose were anomeric. So before all this, before the joining, the anomeric carbons, which one were they? They were C1 of alpha D glucopyranose and they were C1 of beta D fructofuranose. Now, why are we highlighting these two anomeric carbons is because when the sucrose is being formed, these two anomeric carbons are being lost. As you can see that these two will no longer behave as anomeric because now we have lost their respective H and the OH, and now they cannot interconvert and show the properties of anomeric carbon. So if I have to convert this sucrose into their respective two monomers, what I can do is I can bring a water molecule. Say I've got a water molecule HOH, and you can clearly see if I break this bond in this particular form, OH and the OH goes to the respective places. And this is how we can see that they are nothing but the product of hydrolysis. So now we have decided on the anomeric carbons in the previous alpha D glucose and beta D fructose. So now in this sucrose, there is one point that needs attention, that is in sucrose. Now, sucrose was a disaccharide, that is the first point of it. But the main point of highlight here is that when Tollens reagent come in contact, so Tollens reagent test as well as the Felling solution test solution test. Now, both these tests in sucrose are negative. So sucrose will not give the tolerance reagent test as well as the Felling solution test because it does not contain any anomeric carbon, does not contain any group which can convert into an aldehyde to give us these respective tests. Also, since both these tests are negative, so sucrose now becomes a non-reducing sugar. We did the two categories of sugar, in which we saw that any carbohydrates which were reducing both the tolerance and the Felling solution test were reducing sugars, and now we saw sucrose which is not giving both these tests and therefore is called a non-reducing sugar. So the points of highlight of sucrose is, firstly, it is a disaccharide, then it is made up of two monomers, that is alpha D glucopyranose and beta D fructofuranose. These are the two monomers. If we write the name more correctly, then both the tests, the tolerance and the Fellings, is negative and therefore it is known as a non-reducing sugar. Also, it has a glycosidic linkage, that is an ether linkage between two monosaccharides units. So these are the points of highlight which we can see in our sucrose, which is a disaccharide.